Now, in this lecture, we will find out the length of line segment X using two different methods. In the drawing, we have a semicircle inside a quarter circle. We know that side AO equals to 6 units, and side AC is tangent, or tangent AC is tangent to the semicircle at this point. And we want to find out the length of line segment AC that is actually equals to X. So we start with the first method, and we will define the point of tendency of tangent AC with the semicircle as point D. We will define the center of this semicircle as point P. Line segment AO starts from the center of the quarter circle, that is to say from point O, and ends at point A, that is the point of the quarter circle itself. And this is exactly the definition of a radius. So AO is the radius of the quarter circle, and it is equal to 6 units. And here line segment OB starts from the center of the quarter circle, that is to say from point O, and ends at point B, that is the point of the quarter circle itself. That is to say it is the radius of the quarter circle that is equal to 6 units. So OB equals to 6 units. But line segment OB, it is not only the radius of the quarter circle, but it is also the diameter of the semicircle. So we know that the diameter of this semicircle equals to 6 units, and therefore the radius of the semicircle will be equal to half of it. That is to say the radius will be equal to 6 over 2, that is 3 units. So OP is the radius of the quarter circle, that is to say it equals to 3 units. For the same reason, PB is also the radius of the quarter circle, because of the fact that it starts from point P, that is the center of the semicircle, and ends at point B, that is the point on the semicircle itself. Therefore PB is the radius of the semicircle, that is to say it is equal to 3 units. In the next step, we will join points P and D together by a straight line. Line segment PD is also the radius of the semicircle, because of the fact that it starts from point P, that is the center of the semicircle, and ends at point D, that is the point of the semicircle itself, and this is exactly the definition of a radius. So PD is the radius of the semicircle, that is to say it is equal to 3 units. In the next step, we will join points A and P together by a straight line. And I will present to you a new rule that is actually rule number 1. According to rule number 1, the lengths of two tangents from a common external point to a circle are equal. From a common external point from a common external point to a circle are equal. So I'll read rule number 2 again. According to rule number 2, the lengths of two tangents from a common external point to a circle are equal. So what is the meaning of rule number 2? The meaning of rule number 2 is that if we have this circle and we also have this point P, this point P is an external point of this circle. Why point P is an external point? Because point P is not located inside this circle nor on this circle, but is located outside of this circle. That is to say, point P is an external point of this circle. So if from the external point P we draw two tangents to this circle, so here the first tangent will be this tangent, and the point of tangency of the first tangent with the circle is point A, and we'll draw also the second tangent. We define the point of tangency of the second tangent with this circle as point B. And according to rule number 1, the length of two tangents, the length of the first tangent is PA, and the length of the second tangent is PB. And according to rule number 1, the length of two tangents from a common external point, that is to say the common external point is point P, to a circle, to points A and B, are equal. That is to say, PA is equal to PB. So whenever you draw two tangents to a circle from a common external point of that circle, like in this drawing, then the lengths of those two tangents will be equal to each other. In this case, PA is equal to PB. Okay? PA equals to PB. So we can implement rule number 1 in our drawing. In our drawing, we have the common external point A, and from the common external point A, we have two tangents to the semicircle. The first tangent is tangent AO. Tangent AO is tangent to this circle at point O. Point O is the point of tangency. And the second tangent is tangent AC. Is tangent AD. Tangent AD is tangent to this semicircle at point D. Point D is the point of tangency. Then, according to rule number 1, the lengths of those two tangents are equal to each other. That is to say, AO equals to AD, according to rule number 1. We write it now. AO is equal to AD, according to rule number 1. I'll repeat again. AO is equal to AD according to rule number 1, but AO equals to 6 units according to what is given in the question. AO equals to 6 units according to what is given us in the question. So from this equation, 6 equals to AO equals to AD, we derive that AD is also equals to 6 units. Okay, AD is also equals to 6 units. So here you can write down that AD this line segment AD is equal to 6 units. In the next step, we prove that those two right grain triangles can congruent to each other. They can congruent to each other according to side rule. Okay, I write it down. Actually, triangle AOP, this right grain triangle AOP, congruent, this is the sign of congruent, to triangle APD, this triangle, according to side rule. Okay. So actually, side AO equals to side AD equals to 6 units. Side AP is a common side, it belongs to both triangles, so AP equals to itself. It's a common side that belongs to both triangles. And finally, side OP equals to side PD equals to 3 units. That is to say, triangle AOP can congruent to triangle APD according to side rule. And from the fact that those two right great triangles can congruent to each other, we will conclude that those two angles they are equal to each other. That is to say, angle OAP equals to angle PAD and if we define angle OAP as theta, so here angle OAP equals to theta according to our definition. So from this equation angle OAP equals to theta. So from this equation theta equals to angle OAP equals to angle PAD, we conclude that angle PAD is also equals to theta. So actually, those two angles, they're equal to each other, they're both equal to theta, therefore they're equal to each other. In the next step, we will focus on triangle AOP. In this triangle AOP, it is a right triangle. Here, this angle AOP is a right angle because of the fact that in a quarter circle, O is the center of the quarter circle, and this angle is always equals to 90 degrees. Okay, this angle equals to 90 degrees. Therefore, triangle AOP is a right triangle. Okay, so we focus on the right triangle AOP. In the right triangle AOP, we know that tangent alpha, tangent theta equals to OP over AO, or OP over OA. OP over OA. Here, OP equals to 3 units, and AO equals to 6 units according to what is given in the question. And 3 over 6 is 1 over 2. In conclusion, found out that tangent theta equals to 1 over 2. Okay, tangent theta equals to 1 over 2. In the next step, I will present to you the law of cosines, and we will implement the law of cosines in triangle AOC. So first of all, we will join together points O and C by a straight line. So we will implement the law of cosines on this triangle AOC. So first of all, I will present to you the law of cosines. So what is the law of cosines? The law of cosines is true in any triangle. So if we have triangle ABC, this could be any triangle. This is triangle ABC. And we know that side AB of triangle ABC equals to A units in its length. Side AC equals to B units in its length, and side BC equals to C units in its length. And the angle between side AB and side AC is theta. Then, according to the law of cosines, we will get that C squared equals to A squared plus B squared minus 2 times A times B times times cosine theta. I repeat again. In triangle ABC, C square equals to A square plus B square minus 2 times A times B times cosine theta. So you can implement the law of cosines in triangle AOC. So I will copy triangle AOC in this new page and we will implement the law of cosines in triangle AOC. So what is the length of side OC? Point O is the center of the quarter circle. Point C is the point of the quarter circle itself. This is exactly the definition of a radius. That is to say, OC is the radius of the quarter circle that is equal to 6 units. So OC equals to 6 units. And the angle between side OA and side AC is 2 theta. And side AC is the side that we are looking for, that is equal to x according to what is given in the question. So we will implement the law of cosines in this triangle AOC. In this triangle AOC, according to the law of cosines, we will get that this will be question number 1. We will get that OC squared equals to AO squared plus AC squared minus 2 times AO times AC times cosine 2 theta. I'll repeat again. According to the law of cosines in triangle AOC, we get that OC square equals to AO square plus AC square minus 2 times AO times AC times cosine 2 theta. Okay, so here OC equals to 6 units. Therefore, OC squared is 6 squared, that is 36. And it is equal to AO squared. AO equals to 6 units, so AO squared is 6 squared, that is also 36. Plus AC squared. AC equals to x, so AC squared is x squared. Minus 2 times AO is 6. Times AC is x times cosine 2 theta. So here we have 36 on both sides of equation number 1, so 36 will get cancelled. And according to equation number 1, here we have 0, that is equal to x squared minus 2 times 6 is minus 12, so this expression in conclusion is equal to minus 12 x cosine 2 theta So here we will add 2x cosine 2 theta to this equation, equation number 1, and we get that according to equation number 1, x times cosine 2 theta equals to x squared. Here we will divide this equation, equation number 1, by x. We can divide the equation by x because x is the length of side AC. It must be a positive number. It can never be equal to 0. And that is the reason that it is allowable to divide equation number 1 by x. So we divide equation number 1 by x and we get that x over x is 12. So 12 times cosine 2 theta, that is equal to x squared over x is x. So in conclusion, we found out that according to equation number 1, 12 times cosine 2 theta equals to x. So the only thing that is left to do in order to find out the value of x is to find out the value of cosine 2 theta. Actually, we have trigonometric identity for cosine 2 theta according to the following trigonometric identity. Cosine 2 theta equals to 1 minus tangent square theta over 1 plus tangent square theta. Okay? Actually, we have already found out that tangent theta equals to 1/2. Tangent theta equals to 1/2. That is to say, we can substitute tangent theta in this trigonometric identity by 1/2. We'll do it now and we'll get that according to this trigonometric identity, cosine 2 theta equals to 1 minus tangent square theta. Tangent theta equals to 1/2. So tangent square theta equals to 1/2 squared over 1 plus tangent square theta. That is equal to 1/2 squared. Okay? Here it is cosine 2 theta equals to 1 minus 1/2 squared is 1/4 over 1 plus 1/2 squared is 1/4. So in conclusion, we found out that cosine 2 theta equals to 1 minus 1/4 is 3/4 over 1 plus 1/4 is 5/4. So here we have 4 in the numerator and 4 in the denominator, so 4 will get cancelled And we found out that cosine 2 theta equals to 3/5. Cosine 2 theta equals to 3/5. Now we can substitute cosine 2 theta in equation number 1 by 3/5. Here, according to equation number 1, 12 times cosine 2 theta equals to 3/5. So we substitute cosine 2 theta by 3/5. Here, cosine 2 theta, 12 times cosine 2 theta, according to equation number 1, equals to x. So we substitute cosine 2 theta by 3/5 in this equation, equation number 1, and we will get that 12 times cosine 2 theta, that is 3/5, equals to x. So according to equation number 1, 12 times 3 is 36 over 5, that is equal to x. So x equals to 36 over 5, that is 7.2 units. Okay, in conclusion, we found out that x, the line segment that we are looking for, it is equal to 7.2 units. Here, side AC that is equal to x, it is equal to 7.2 units. Okay, we finished with the first method. In the next step, I will present to you how to find out the length of line segment AC that is equal to x according to the second method. Okay. In the second method, we'll use all the things that we have already found out in the first method. The center of the semicircle is at point P. The point of tendency of tangent AC with the semicircle is at point D. OP is the radius of the semicircle, that is 3 units. PB also is the radius of the semicircle, that is also 3 units. And here, PD is also the radius of the semicircle, that is to say it is also equals to 3 units. Here, we have already found out that this again equals to 90 degrees. We have already found out that triangle AOP is congruent to triangle APD. I write it down. According to triangle AOP, it can go into triangle APD according to angle similarity rule. And from that fact, we actually conclude that those two angles are equal to each other. Angle AOP is equal to angle PAD according to the rule that corresponding angles in congruent triangles are equal to each other, and if angle PAD equals to theta, angle PAD equals to theta, then from this equation angle OP equals to angle PAD equals to theta, we will derive that angle AOP is also equals to theta. So those two angles, they are both equal to theta. So until this step, we did all these things in the first method. In the next step, we will do in the second method another construction. Here we will extend line segment AC by a straight line, and we will also extend line segment OB by a straight line. We will extend those two line segments by a straight line until they intersect with each other. Okay? And we will define the intersection point of the two line segments, the two extended line segments, as point E. Point E is the intersection point of the two extended line segments, AC and OB. Actually, we created here the right triangle AOE. AOE is the right triangle because this angle equals 90 degrees. So we copy the right triangle AOE in a new page. In this right triangle AOE, AP is angle bisector of angle OAE. The angle bisector AP bisects angle OAP into two halves. The first half is theta and the second half equals also to theta. Okay, so we copy the right triangle AOE in a new page, and we will implement the angle bisector theorem in the right triangle, triangle AOE. This is the right triangle AOE. That's a copy from the original drawing. Here, AP is angle bisector of angle OAE in the right triangle AOE. And we actually have the angle bisector theorem according to angle bisector theorem. If we have triangle ABC, that could be any triangle, and here AD is angle bisector of angle BAC. So this is angle bisector theorem. Angle bisector theorem. According to angle bisector, and AD is the angle bisector. In the right angle ABC, AD is angle bisector. So, according to the angle bisector theorem, the angle bisector of a triangle in this case is AD, divides the side that it hits in a ratio that is equal to the ratio of the angles legs. So I read the angle bisector theorem again. According to angle bisector theorem, the angle bisector of a triangle divides the side that it hits in a ratio that is equal to the ratio of the angle's legs. So here, actually, we are talking about the angle bisector AD, and according to angle bisector theorem, the angle bisector AD divides the side that it hits. Angle bisector AD hits side BC, and it divides it into two parts. The first part is BD, and the second part is DC. And the ratio between those two parts, that is to say BD over DC, equals to the ratio of the angle's legs. And the angle's legs are AB and AC, and the ratio between the angle's legs is AB over AC. In conclusion, according to angle ratio theorem, AB over AC equals to BD over DC. Okay? So here we can implement the angle bisector theorem in triangle AOE according to the angle bisector theorem. In the right triangle AOE, we have AP is the angle bisector, so it divides the side that it hits, that is to say, it hits side OE, and it divides it in a ratio that is equal to OP over PE. And that ratio equals to the ratio between the angles legs. The angles legs are AO and AE, and the ratio between the angles legs is AO over AE. So in conclusion, we found out, this will be question number 1. We know that OP is the radius of the semicircle, that is to say it is equal to 3 units. You can see here that OP equals to 3 units. It is the radius of the semicircle. So according to equation number 1, OP is 3 over PE equals to AO is 6 over AE. So according to equation number 1, 3 over PE equals to 6 over AE. We will divide equation number 1 by 3 and we will multiply it by AE, and we'll get that according to equation number 1, AE over PE equals to 6 over 3. 6 over 3 is 2. So I found out that AE over PE, according to equation number 1, equals to 2. We'll multiply the equation number 1 by PE, and we'll get that according to equation number 1, AE equals to 2 times PE. So if we define PE as A, here PE equals to A according to our definition. Then, according to equation number 1, we get that AE equals to 2 times PE, and PE is A, so AE equals to 2 times PE, that is A, so it is 2A. AE equals to 2A. So I actually found out that AE equals to 2A, and according to our definition, PE equals to A. So in the next step, we'll continue to focus on the right triangle AOE, and in the right triangle AOE, we will implement the Pythagoras theorem. So I'll copy the right triangle AOE again, and we will implement the Pythagoras theorem of the right triangle AOE. Okay? So we have the right triangle AOE. Side AO equals to 6 units. AE equals to 2A. What is the length of side OE? side OE equals to 3 plus PE. So side OE, I write it down. Side OE equals to 3 plus PE. That is to say, side OE equals to 3 plus PE equals to A according to our definition. So we substitute PE by A, and we get, in conclusion, that side OE equals to 3 plus A. So now we will implement the Pythagoras theorem on the right triangle AOE. By PT is the evaluation for Pythagoras theorem. The square of the hypotenuse equals to the sum of the squares of the perpendiculars. This will be equation number 2. The square of the hypotenuse is AE, so the square of the hypotenuse is AE squared. And it is equal to the sum of the squares of the perpendiculars. That is to say, it is equal to AO squared plus OE squared. Okay, so here according to equation number 1, AE squared, A equals to 2A, so A squared equals to 2A squared. And it is equal to AO squared. AO equals to 6, so AO squared is 6 squared, that is 36, plus OE squared. OE equals to 3, OE equals to 3 plus A, so OE squared equals to 3 plus A squared. So here we will open the brackets on both sides of this equation. It is actually equation number 2. This is equation number 2. We will open the brackets on both sides of equation number 2, and we get that according to equation number 2, 2A squared is 4A squared equals to 36 plus 3 plus A squared equals to 3 squared, that is 9, plus A squared plus 6A 36 plus 9 is 45, plus A squared plus 6A equals to 4A squared. We subtract A squared from this equation, equation number 2, and we get that according to equation number 2, 3A squared minus A squared is 4A squared minus A squared is 3A squared. And it is equal to, here A squared minus A squared is 0, so it is 45 plus 6A. Here we divide this equation, equation number 2 by 3, and we get that according to equation number 2, 3A squared, 3 is A squared, and it is equal to 45 over 3 is 15, plus 6A over 3 is 2A. So in conclusion, we found out that according to equation number 2, A squared equals to 15 plus 2A. We subtract 15 and also 2A from this equation, equation number 2, and we will get that according to equation number 2, A squared minus 2A minus 15 equals to 0. So we have here a quadratic equation. In this quadratic equation, the coefficient A equals to 1. The coefficient B equals to minus 2. The coefficient C equals to minus 15. And the variable that you are looking for in this quadratic equation is a, so x equals to a. And the general formula for a solution of a quadratic equation is x equals to minus b plus minus square root of b squared minus 4 times a times c over 2a. In our specific quadratic equation, x equals to a, so we substitute x by a. A equals to, according to this specific solution for a quadratic equation, we get that a equals to minus b equals to minus 2. So minus b is minus 2, that is 2, plus minus square root of b squared. B is minus 2, so b squared is minus 2 squared, that is 4. Minus 4 times a is 1, times c, that is minus 15, over 2a. A is 1, so 2 times 1 is 2. So here we get that a equals to 2 plus minus square root of minus 4 times minus 15 is 60, and 60 plus 4 is 64. So inside the root we left only with 64 divided by 2. So we get here that a equals to 2 plus minus the square root of 64 is 8 over 2. So here we will have two solutions that are possible for a. The first solution for a is that a equals to on a1 it is equal to 2 minus 8 over 2. 2 minus 8 is minus 6, and minus 6 over 2 is minus 3. So in conclusion, we found out that a1 equals to minus 3. But you can see in the drawing that a is the length of side PE, and a as a length must be a positive number. A is a length, therefore it must be a positive number. It can never be equal to minus 3. So we cancel the solution, and we left only with the second solution. a2 equals to 2 plus 8 over 2. 2 plus 8 is 10, and 10 over 2 is 5. So we found out that a2 equals to 5. So we can write here that a equals to 5 units. 2a is 2 times 5, that is 10, so a equals to 10 units. And what is the value of line segment BE? From the drawing it is very easy to see that the length of line segment BE, it is equals to PE minus PB. PE minus PB equals to BE. I repeat again that BE equals to PE minus PB. Here we have already found out that P equals to A. P equals to A, that is equal to 5 units. And PB equals to 3 units. This is the radius of the semicircle. So in conclusion, found out that B equals to 5 minus 3, that is 2 units. So B equals to 2 units. here VE equals to 2 units. And what is the length of line segment CE? The length of line segment CE, it is very easy to see from the drawing that the length of line segment CE, it is equals to AE minus AC. Again, AE minus AC equals to CE. AE minus AC. I repeat again that for the drawing it is very easy to see that C equals to AE minus AC. So CE equals to AE equals to 10 units. This 2A and 2A equals to 10. AC equals to X, it is the line segment that we are looking for. So in conclusion, we found out that CE equals to 10 minus X. Okay? C equals to 10 minus X, so we can write here that C equals to 10 minus X. In the next step, I will present to you a new rule that is actually rule number 3. According to rule number 3, if two chords intersect with each other outside the circle, then the following equation is true. So we have here point P. This is the intersection point between the two chords. That is to say, they intersect with each other externally, that is to say, outside the circle. Okay? So here, the first chord is called A, B, and the second chord is called CD. I repeat again that chord AB and chord CD intersect with each other at point P. Point P is the intersection point of chord AB with chord CD. Then the following equation is true, that PA times PB is equal to PC times PD. Okay, so I'll read rule number 3 again. According to rule number 3, if two chords intersect with each other outside the circle, then the following equation is true, that PA times PB equals to PC times PD. So here, chord AB intersects with chord CD at point P. Point P is the intersection point of chord AB with chord CD that is outside the circle. So in this case, the following equation is true, that PA times PB equals to PC times PD. Again, PA times PB equals to PC times PD. So we can actually implement rule number 3 in our drawing. But before that, we will complete the quarter circle to a circle. So here we completed the quarter circle to a circle. In the next step, we will extend line segment BO by a straight line until it intersects with the circle, or until it touches circle, and we'll define the touching point of the extended line segment BO and the circle as point M. Point M is the touching point or the intersection point of the extended line segment BO and this circle. So what is the length of MO? The length of MO, O is the center of the circle and also the center of the quarter circle. M is the point of the circle itself, and this is exactly the definition of a radius. That is to say, OM is the radius of the quarter circle and also the radius of the circle itself. That is to say, it is equal to 6 units. So now we have here chord BM that intersects with chord AC at point E. Point E is the intersection point of those two chords. Therefore, according to rule number 3, we will get that EC times EA equals to EB times EM. I repeat again, because of the fact that in our drawing we have two chords that intersect with each other outside the circle. That is to say, the two chords intersect with each other at point E, that is a point that is outside the circle. Then according to rule number 3, we get that EC times EA equals to EB times EM. Okay, so here EC equals to 10 minus X, EA equals to 10 units according to what we have already found out, and it is equal to EB equals to 2 units, and EM, the long line segment EM equals to 6 plus 3 plus 3, that is 12, plus 2, that is 14. In conclusion, EM equals to 14. So in conclusion, we found out that 10 minus X times 10 equals to 2 times 14, that is 28. So 28 equals to 10 times 10 minus X. Here we divide this equation by 10. And we get that according to this equation, 10 minus X equals to 28 over 10 is 2.8. We will add X to this equation and we will subtract 2.8, and we get that according to this equation, X equals to 10 minus 2.8. That is to say, X equals to 7.2 units. So we found out that according to the second method also, X, the line segment that we are looking for, it is equal to 7.2 units. X, that is actually AC, it is equal to 7.2 units. Okay, we finished with the second method. In the next step, I will summarize the lecture. We will start with the first method. So I will repeat on the question itself. In the drawing, we have a semicircle that is described by a quarter circle. We know that side AO equals to 6 units, and we want to find out the length of side AC that is actually equals to X. So first of all, we defined the point of tendency of tangent AC with this semicircle as point D. We define the center of this semicircle as point P. O is the center of the semicircle, and this angle must be equal to 90 degrees. Angle OAB must be equal to 90 degrees because this is a quarter circle, and AO must be the radius of the quarter circle that is equal to 6 units. OB is line segment that it starts from the center of the quarter circle and ends at point B, that is the point of the quarter circle itself. That is to say, this is exactly the definition of a radius. That is to say, OB is the radius of the quarter circle that is equal to 6 units. But OB, it is not only the radius of the quarter circle, but it is also the diameter of the semicircle. So we know that the diameter of the semicircle equals to 6 units, and the radius must be equal to half of the diameter. So if the diameter equals to 6 units, it means that the radius equals to 6 over 2, that is 3 units. So OP equals to PB equals to PD equals to 3 units because of the fact that all the 9 segments here are the radii of the semicircle, that is to say they are equal to 3 units. Then I presented, we joined points A and P together by a straight line, and then I presented to you rule number 1. According to rule number 1, the lengths of two tangents from a common external point to a circle are equal. So what is the meaning of rule number 1? The meaning of rule number 1 is that if we have this circle and we have the point P that is the external point of this circle, and from the external point P we draw two tangents to this circle. The first tangent is tangent PA, the second tangent is tangent PB. Then the lengths of those two tangents will be equal to each other. That is to say, PA will be equal to PB. So whenever you draw two tangents to a circle from a common external point to that circle, then the lengths of those two tangents will be equal to each other. We can implement rule number 1 in our drawing, because in our drawing we have the common external point, point A, in relation to the semicircle. Point A is the common external point, and from the common external point, point A, we have two tangents to this semicircle. The first tangent is tangent AO. Tangent AO is tangent to this circle at point O, to this semicircle at point O, and tangent AD is tangent to this semicircle at point D. Point D is the point of tendency of tangent AD with this semicircle, and according to rule number 1, the lengths of those two tangents will be equal to each other. That is to say, AO equals to AD according to rule number 1. Okay, AO equals to AD according to rule number 1. But according to what is given us the question, AO equals to 6 units. So we can write here that AO equals to 6 units. And from this equation, 6 equals to AO equals to AD, we will derive that AD is also equals to 6 units. Yeah, okay, AD is also equals to 6 units. And then, now, the two green triangles can go into each other according to side rule. I repeat again, triangle AOP can go into triangle APD according to side rule. I will explain why they can go into each other. First of all, AO equals to AD equals to 6 units according to rule number 1. AP is a common side that belongs to both triangles, so AP equals to itself. AP is a common side. And OP equals to PD equals to 3 units. This is the radius of the semicircle. So all the sides of triangle APD can go into all the sides of triangle ADP. Therefore, those two triangles can go into each other according to side rule. Very simple. And from the fact that those two triangles can go into each other, we will conclude that those two angles are equal to each other. That is to say, angle OAP equals to angle PAD according to the rule that corresponding angles in congruent triangles are equal to each other. Those two green triangles can go into each other. Therefore, those two angles that are corresponding angles must be equal to each other. That is to say, angle OAP equals to angle PAD. And if we define angle OAP as theta, then from this equation theta equals to angle OAP equals to angle PAD, we will derive that angle PAD is also equals to theta. So those two angles, they are both equal to theta, therefore they are equal to each other. Then we focused on triangle AOP, on the right green triangle AOP. We know that tangent theta equals to OP over OA. In the right triangle AOP, tangent theta equals to OP over OA. OP equals to 3 units. OA equals to 6 units. So tangent theta equals to 3 over 6. That is actually 1 over 2. So we found out that tangent theta equals to 1 over 2, 1 half. Tangent theta equals to 1 half. Okay, then I presented to you the law of cosines that I've already mentioned it in the previous lecture, and we implemented the law of cosines in triangle AOC. So we connected together points O and C, and in this way we created triangle AOC, and we implemented the law of cosines in the triangle AOC. What is the law of cosines? First of all, the law of cosines is true in any triangle, so we can write here that in any triangle, here triangle ABC could be any triangle. We know that side AB of triangle ABC equals to A units, side AC of triangle ABC equals to B units in its length, and side BC equals to C units in its length. Then, and the angle between side AB and side AC is theta. Then, according to the law of cosines, we get that C squared equals to A squared plus B squared minus 2 times AB times AC times cosine theta. Okay, this equation is true in any triangle. So we implemented the law of cosines in triangle AOC. I copied triangle AOC in this new page, and we implemented the law of cosines in triangle AOC. Here, according to the law of cosines, we get that OC squared equals to AO squared plus AC squared minus 2 times AO times OC times cosine 2 theta. OC equals to 6 units, so OC squared is 6 squared, that is 36. AO also equals to 6 units, so AO squared is 6 squared, that is also 36. AC equals to X, so AC squared is X squared. Minus 2 times AO is 6 and AC is X, so it is minus 2 times 6 times X times cosine 2 theta. So here we have 36 on both sides of equation number 1, so 36 will get cancelled, and we left only with 0, that is equal to X squared. Minus 2 times 6 is minus 12, so this expression equals to minus 12x cosine 2 theta. We added 12x cosine 2 theta to this equation, equation number 1, and we found out that according to equation number 1, 12x cosine 2 theta equals to x squared. Here we divided this equation number 1 by x, and we found out that 12 cosine 2 theta equals to x. The only thing that is left to do in order to find out the value of x, the line segment that we are looking for, is to find out the value of cosine 2 theta. We have trigonometric identity for cosine 2 theta. According to this trigonometric identity, cosine 2 theta equals to 1 minus tangent square theta over 1 plus tangent square theta. We have already found out that tangent theta equals to 1 half. So we can substitute tangent theta in this trigonometric identity by 1 half. We did it, and we got that cosine 2 theta equals to 1 minus tangent square theta. Tangent theta equals to 1 half. So tangent square theta will be equal to 1 half squared. So in the numerator we have 1 minus 1 half squared over 1 plus tangent square theta, that is equal to 1 half squared. So in conclusion, cosine 2 theta equals to 1 minus 1 half squared over 1 plus 1 half squared. 1 half squared is 1 quarter, so here it is 1 minus 1 quarter, and here in the denominator we have 1 plus 1 quarter. 1 minus 1 quarter is 3 quarters, and 1 plus 1 quarter is 5 quarters. So in conclusion, we got that cosine 2 theta equals to 3 quarters over 5 quarters. Here we have 4 in the numerator and 4 in the denominator, so 4 will get cancelled, and we left only with cosine 2 theta that is equal to 3 over 5. So I found out that cosine 2 theta equals to 3 fifths. Now we can substitute cosine theta in equation number 1 by 3/5. We did it, and we got that according to equation number 1, 12 times cosine 2 theta equals to x. We substituted cosine 2 theta by 3/5, and we got that here x equals to 12, and cosine 2 theta is 3/5. So we substitute cosine 2 theta by 3/5, and it is equal to x. So in conclusion, according to equation number 1, 12 times 3/5 equals to x. Here 12 times 3 is 36, and so in conclusion, this expression equals to 36 over 5. So x equals to 36 over 5, and 36 over 5 is 7.2 units. So we found out that the length of line segment AC that is equal to x, it is equal to 7.2 units. We finished with the first method. In the next step, I will present to you how we found out the length of line segment AC that is equal to x according to the second method. In the second method, we used all the things that we have already found out in the first method, and here this angle equals to 90 degrees, OP equals to 3 units, PB equals to 3 units, PD equals to 3 units. Those two right triangles can go into each other according to side rule. So actually, triangle AOP can go into triangle APD according to side rule. Therefore, we can derive from it that angle AOP equals to angle PAD. Those two angles are equal to each other. So if we define angle PAD as theta, angle PAD equals to theta, then from this equation we derive that angle AOP also equals to theta. So those two angles are both equal to theta. Okay? Then we did another construction in the second method. We extended line segment AC by a straight line, and we extended line segment OB by a straight line until they intersect with each other at point E. Point E is the intersection point of the extended line segment AC and the extended line segment OB. In this way, we created the right triangle, triangle AOE. Okay? In the right triangle AOE, AP is angle bisector, that is to say it bisects angle OAE into two halves. The first half equals to theta, and the second half also equals to theta, of course. Now we can implement the bisector, the angle bisector theorem on the right triangle AOE. So what is angle bisector theorem? The angle bisector theorem states that if we have this triangle ABC, that could be any triangle, and we have line segment AD is angle bisector of angle BAC. Why? Because it divides angle BAC into two halves. The first half is equal to theta, and the second half also equals to theta. So, according to angle bisector theorem, the angle bisector of in a triangle divides the side that it eats in a ratio that is equal to the ratio of the angle legs. So here, according to angle bisector theorem, the angle bisector AD divides the side that it eats. Angle bisector AD each side BC, and it divides it into two parts, BD and DC. And the ratio between those two parts is BD over DC. And this ratio, according to Eigenvalue theorem, equals to the ratio between the angles legs. And the angles legs are AB and AC. And the ratio between the angles legs is AB over AC. So AB over AC, that is the ratio between the angles legs, equals to the ratio that angle bisector AD divides side BC. That is BD over DC. That is to say, BD over DC equals to AB over AC. Okay? Again, the angle bisector AD divides side BC in a ratio that is equal to BD over DC, and this ratio equals to the ratio between the angles legs, that is AB over AC. That is to say, AB over AC equals to BD over DC. We can implement the angle bisector theorem in our triangle AOE, because we have a line segment AB that is angle bisector of angle OAE. According to angle bisector theorem, we will get that the angle bisector AP divides the side that it is, that is side OE, in a ratio that is equal to OP over PE, and this ratio equals to the ratio between the angles legs, and the ratio between the angles legs is AO over AE, very simple. Okay, so in conclusion, we found out that OP over PE equals to OA over AE. OP equals to 3 units. PE is PE, OA equals to 6 units, and AE equals to AE. So in conclusion, we found out that 3 over PE equals to 6 over AE. Here we divided the equation number 1 by 3, and we multiplied it by AE, and we found out that AE over PE equals to 6 over 3. 6 over 3 is 2, so in conclusion we found out that AE over PE equals to 2. We multiplied the equation number 1 by PE and found out that according to equation number 1, AE equals to 2 times PE. So if we define PE as A, here, PE equals to A according to our definition, now we can substitute PE in equation number 1 by A. We substituted PE by A, and we got that according to equation number 1, AE equals to 2 times PE, and PE is A, so AE equals to 2A. So in conclusion, we found out that AE equals to 2A. Okay? So A equals to 2A, and P equals to A according to our definition. Okay? Then we continued to focus on the right triangle AOE, and we implemented the Pythagoras theorem on the right triangle AOE. So I copied the right triangle AOE in this new page. We have already found out that A equals to 2A. AO equals to 6 units according to what is given as the question. This angle equals to 90 degrees because we are talking about a quarter circle. And what is the length of OE? OE equals to OP plus PE. Again, OE equals to OP plus PE. But OP equals to 3 units. P equals to A. So in conclusion, we found out that O equals to 3 plus PE, and P equals to A. So in conclusion, O equals to 3 plus PE, that is A. So in conclusion, O equals to 3 plus A. So we implemented the Pythagoras theorem. PT is the abbreviation for Pythagoras theorem in the right triangle AOE. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. That is to say, the square of the hypotenuse is AE squared, and it is equal to AO squared plus OE squared. AE equals to 2A, so A squared is 2A squared. AO equals to 6, so AO squared is 6 squared, that is 36. And it is plus OE squared. OE is 3 plus A, so OE squared is 3 plus A squared. So in conclusion, we found out that according to equation number 2, 2A squared equals to 36 plus A plus 3 plus 3 plus a squared. We open the brackets on both sides of equation number 2 and found out that according to equation number 2, 2a squared is 4a squared. That is equal to 36, and a plus 3 squared equals to 3 plus a squared equals to 3 squared, that is 9, plus a squared plus 6a. 36 plus 9 is 45. So in conclusion, we found out that 4a squared equals to 45 plus a squared plus 6a. We subtracted a squared from equation number 2. So 4a squared minus a squared is 3a squared. A squared minus a squared is 0. So in conclusion, we found out that 3a squared equals to 45 plus 6a. We divided this equation number 2 by 3, and we got that 3a squared over 3 is a squared, 45 over 3 is 15, and 6a over 3 is 2a. So in conclusion, we found out that according to equation number 2, a squared equals to 15 plus 2a. Okay, we subtracted 15 and also 2a from this equation number 2, and we got, according to equation number 2, the quadratic equation that a squared minus 2a minus 15 equals to 0. In this quadratic equation, the coefficient a equals to 1, the coefficient b equals to minus 2, and the coefficient c equals to minus 15. And the variable that we are looking for in this quadratic equation is a, so x equals to a, and the general formula for solving a quadratic equation is x equals to minus 3 plus minus square root of b squared minus 4 times ac over 2a. So here x equals to a, so a equals to minus b, b equals to minus 2. So minus b is minus 2, that is plus 2. Plus minus square root of b squared. B is minus 2, so b squared is minus 2 squared, that is 4. Minus 4 times a is 1, times c, that is minus 15. So in conclusion, it is minus 4 times minus 15. Over 2a, that is 2. Because a equals to 1, 2 times 1 is 2. So here we have a equals to 2 plus minus. Minus 4 times minus 15 is plus 60. And 60 plus 4 is 64. So in conclusion, we found out that a equals to 2 plus minus square root of 64 over 2. Square root of 64 is 8. So in conclusion, we found out that a equals to 2 plus minus 8 over 2. So here we will have two solutions that are possible for a. The first solution for a is a1, that is equal to 2 minus 8 over 2. 2 minus 8 is minus 6, and minus 6 over 2 is minus 3. But because of the fact that a is the length of side PE, it must be a positive number. It's a length, it must be a positive number. A is a length, and it must be a positive number, therefore it can never be equal to minus 3, that is a negative number. So we cancel this solution, and we left only with the second solution for a, that a equals to 2 plus 8 over 2. 2 plus 8 is 10, and 10 over 2 is 5. So in conclusion, we found out that a equals to 5 units. So here we can write down that a equals to 5, therefore 2a is 2 times 5, that is 10. A equals to 10, p equals to a, that is 5. And then we found out the length of line segment BE. From the drawing, it is very easy to see that BE equals to here PE minus PB. Again, PE minus PB equals to BE. Okay? Here BE equals to PE minus PB. PE equals to A, that is 5. PB equals to 3, that is the radius of the semicircle. So in conclusion, B equals to 5 minus 3, that is 2. So we found out that line segment B equals to 2 units. And then we found out the length of line segment CE. From the drawing, it is very easy to see that the length of line segment CE, it is equals to AE minus AC. AE minus AC equals to CE. C equals to AE minus AC. A equals to 10. AC is X is the variable that we are looking for. So in conclusion, we found out that C equals to 10 minus X. Then I presented to you a new rule that is actually rule number 3. According to rule number 3, if two chords intersect with each other outside the circle, then the following equation is true, that PA times PB equals to PC times PD. So here we have this circle and we have chord AB and chord CD again. Chord AB and chord CD that intersect with each other externally outside the circle. It's point P. Point P is the intersection point of the extended chord BA and the extended chord CD. So in this situation, if we have two chords that intersect with each other outside the circle, like in this drawing, those two chords intersect with each other outside the circle that is point P, then according to rule number 3, we get that PA times PB equals to PC times PD again. PA times PB equals to PC times PD. We can implement rule number 3 in our drawing, but first of all, from the quarter circle, we completed the quarter circle to a circle, and then we extended line segment BO by straight line until it intersects with the circle at point M, or until it touches the circle at point M. So point M is the touching point of the extended line segment BO and the circle. So MO, what is the length of line segment MO? O is the center of the circle and also the center of the quarter circle. M is the point on the circle itself, and this is exactly the definition of a radius. That is to say, OM is the radius of the circle, that is to say, it is equal to 6 units, because the radius of the circle equals to the radius of the semicircle, that is equal to 6 units. So now we can implement rule number 3 in our drawing, because we have chord MB intersects with chord AC, again chord MB intersects with chord AC, and the external point, point E, they intersect with each other outside the circle at point E. Point E is the intersection point of chord AC with chord MB. Therefore, according to rule number 3, we will get that EC times EA equals to EB times EM. Again, according to rule number 3, because we have two chords that intersect with each other outside the circle, according to rule number 3, we get that EC times EA equals to EB times EM. EC equals to 10 minus X. EA equals to 10 units. EB equals to 2 units, and EM equals to 6 plus 3 plus 3, that is 12, plus 2 is 14. So EM equals to 14 units. So in conclusion, we found out that according to rule number 3, EC times EA equals to EB times EM, EC equals to 10 minus X, EA equals to 10, EB equals to 2, and EM equals to 14. So in conclusion, we found out that 10 minus X times 10 equals to 2 times 14. 2 times 14 is 28. So in conclusion, we found out that 10 times 10 minus X equals to 28. We divided this equation by 10 and we found out that 10 minus X equals to 28 over 10, that is 2.8. So 10 minus X equals to 2.8. We added X to this equation and we subtracted 2.8 and we found out that X equals to 2 minus 2.8. X equals to 10 minus 2.8, that is to say it is equals to 7.2 units. So here line segment AC, that is equal to x, equals to 7.2 units. So we arrive to the same answer, that x equals to 7.2 units in both methods. Okay, thank you very much.